The surface of this mirror is so smooth that if we took this 27-foot mirror and then spread it out from coast to coast in the United States, east to west coast, the height of the tallest mountain on that mirror would be about ½ an inch. That's how smooth this mirror is.
The challenge with GMT is 6 of the 7 mirrors are portions of a parabola, but they're off the central axis. And in fact, the central axis is not only off-center in the mirror, it's way outside the mirror itself. So you have to work off-axis, asymmetrically, and yet put in this beautiful surface. We have to make this optic precise enough so that when the light travels 5, 10 billion light years and comes and hits our telescope, that we don't scramble and lose that information that's traveled so long. We have to make these large optics to a 20th of a wavelength of light, even though it's 25 meters across. It's a challenge of about 1 part in 10 billion in terms of precision manufacturing. So it's an extraordinarily challenging process. Right now, we are in the process of developing 4 of the 7 mirrors that go into the telescope. That is, the first mirror is completed. The second mirror, we're grinding away on it. The third mirror, we're building up the mold and we'll start melting the glass in August. And the fourth mirror, the glass and the mold materials are already coming in and being sorted in the warehouse in Tucson.
Each of these mirrors, the glass alone is 20 tons of glass in each mirror. There are 7 of the mirrors. There's a mount made of steel that has to hold the mirrors, the structure, the instruments, the top end of the telescope where there are secondary mirrors. We have to measure the distance between the primary mirror and the secondary mirror to 1 part in 500 million. And then focus light to a fraction of a wavelength of light. It's an astounding, astonishing challenge. And this enclosure will be the height of a 22-story building. It's not an ordinary building. It has to rotate so that you can point the telescope in the sky and look out and see distant objects.
It has cranes, it lifts things, it has air conditioning, it has heating, it has power, it has liquid nitrogen, liquid helium. This is a complicated business, and it's a dance between the telescope and the dome that they all have to play together and work together to make sure the telescope delivers what it was built for.
So all of this elaborate structure that we have to build is really just to receive a small number of photons of light that are coming to us from distant space, hit this small little patch where we've set up these mirrors, and allow us to address these mysteries that we don't yet understand about our universe. It's like Ferdinand Magellan, after whom giant Magellan telescope is named. Here he was coming around Cape Horn. There was a whole other ocean there to be discovered. We don't know what's out there, but we're setting sail to try and discover what's out there.
We've learned in recent years, sort of the past couple of decades, that massive black holes are common, and in fact, almost every galaxy has a giant black hole at its center, and extraordinarily enough, there seems to be a roughly constant fraction of the galaxy's mass in the black hole. So we don't know, did the black hole come first and the galaxy grow around it? Did the galaxy build and the black hole formed after that? Where did all the stuff that went into the black hole come from? Did they grow by merging with other black holes, or did they simply feed, or they go through a gluttonous phase where they swallow stars whole to become so massive? Right now we can only see in any detail a few of those black holes, the ones that are either the nearest or the most massive. GMT, using the power of adaptive optics, will allow us to look at giant black holes almost anywhere in the cosmos, and will allow us to look at the small ones, the seed black holes, very nearby. As we try to track down the mystery objects, the strange beasts, the gamma ray bursters, the neutron stars, things that we haven't discovered yet that will go bump in the night because we don't have good time coverage, that's where we'll stumble upon these new discoveries. Neutron stars were discovered almost by accident. A whole host of phenomena were discovered when we could first look into the infrared. So I expect that as we sleuth along trying to solve the mysteries that we can see, we'll bump into new things.
We are only beginning to scratch the surface, the tip of the iceberg, in learning about planets. How do planets form? Are there other planets in addition to Earth that could have life on them? Right now we have faint images come from the Hubble Space Telescope taking the deepest pictures of the sky that have ever been taken. and we only see faint little smudges. Giant Magellan Telescope will have 10 times the resolution of the Hubble Space Telescope and the ability to take spectra of these most distant objects. We will witness directly the first galaxies forming, the first supernova forming, the first black holes forming, and see how the universe that we're living in now, that we see so directly, came to be. We're now embarking on a new adventure. We're building a telescope that's larger than any in existence. We don't know what discoveries await us, but that's part of the excitement and the challenge of building this new project, this new telescope.